Hello, students. Let me begin with a simple question. Have you ever wondered how your blood maintains almost the same pH no matter what you eat or drink? This is because nature has built-in protective systems called buffers. Buffer solutions are unique. They resist sudden changes in pH even when diluted or when a small amount of acid or base is added. That's why body fluids like blood and urine can function properly only if their pH remains within narrow limits. Without buffers, our vital chemical and biochemical processes would be thrown off balance. In fact, even medicines and cosmetics rely on buffers to keep their formulations effective and safe.
Buffers come in two main types. First, we have acidic buffers, formed by mixing a weak acid with the salt of that acid and a strong base, like acetic acid combined with sodium acetate. Such buffers maintain pH below 7. On the other side, we have basic buffers, created by a weak base and its salt, with a strong acid, like ammonium hydroxide with ammonium chloride. These keep the pH above 7. The beauty of buffers lies in the ratio of the salt to the weak acid or base. This ratio is what sets the actual pH of the solution. To design buffers systematically, chemists use the Henderson-Hasselbalch equation. For an acidic buffer, the pH equals pKa plus the logarithm of the concentration ratio of salt to acid, written as pH equals pKa plus log open bracket salt concentration over acid concentration, close bracket. Similarly, for a basic buffer, we use pOH equals pKb plus log of salt to base ratio. This equation gives us a powerful tool. It tells us how to adjust concentrations to achieve any desired pH. In fact, the equation is the backbone of buffer design in labs, industries, and biological systems. Let's see this in action. Suppose we want a buffer around pH 4.7. We take acetic acid, which has a pKa value of about 4.76, and its salt sodium acetate. If their molar concentrations are equal, the ratio is 1, and the logarithmic term becomes 0. That means the pH of the buffer equals the pKa, or about 4.76. If we add more salt, the pH increases slightly. If we add more acid, the pH decreases. This simple adjustment allows chemists to fine-tune buffer systems with precision. Now imagine we need a buffer in the alkaline range. A classic choice is ammonium hydroxide with ammonium chloride. Here, the relevant expression is pOH equals pKb plus log open bracket salt over base close bracket. For ammonium hydroxide, pKb is around 4.75. That translates to a buffer pH near 9.25. What's fascinating is that dilution does not affect buffer pH, because although concentrations drop, the ratio of salt to base remains unchanged. This makes buffers stable and reliable even when solutions are diluted in practical applications. Let's solve a quick example together. Suppose we prepare a buffer with 0.1 molar acetic acid and 0.1 molar sodium acetate. Using the Henderson-Hasselbalch equation, pH equals pKa plus log open bracket salt concentration over acid concentration close bracket. Substituting, pH equals 4.76 plus log of 0.1 over 0.1. Since the ratio is 1, log 1 equals 0, so the pH comes out as 4.76. This confirms that when the acid and its salt are present in equal concentrations, the buffer pH matches the pKa value of the acid. A neat and elegant calculation. To wrap up, let's see why buffers matter so much. Your blood maintains a pH close to 7.4 thanks to the carbonic acid bicarbonate buffer system. In fermentation, pharmaceutical formulations, and cosmetics, buffers stabilize the environment so processes run smoothly. In industries like dyeing, electroplating, and even photography, buffers regulate pH with precision. So, to summarize, buffers are solutions that resist pH changes. They are designed using the Henderson-Hasselbalch equation, and they are vital in biology, medicine, and technology. Without buffers, our chemical world would be far more unstable. I hope this session gave you a clear and fascinating insight into buffer solutions. Catch you in the next class with more exciting chemistry concepts that connect directly to life around us.